Hi, my name is Yashwant. I am going to discuss the emergence of silicon photonics and optical integration in the recent years. Interest in the field of silicon photonics, especially silicon lasers, has gained importance largely due to its applications in high data transfer rates in interconnects. Optical sensors also have gained importance since they are very sensitive and can easily detect changes. Silicon, being an indirect bandgap material, makes it difficult to initiate lasing action. This is due to the fact that there is a very less chance for radiative recombination, which is essential for lasing. The main advantage of using silicon as a substrate is its high purity and low defect density. It's also easier to fabricate micrometer range components using silicon. As you can see, there are different types of silicon lasers. To name a few, we have Raman lasers, epitaxial lasers, and hybrid lasers. Silicon Raman lasers or Raman lasers work on the principle of Raman effect. We use stimulated Raman effect to make flexible lasers. We use a pump with energy around silicon bandgap which can help reduce free carrier absorption. This power is around a few watts. Such high powers could lead to another loss mechanism known as two-photon absorption or TPA. This TPA increases with the number of photons and hence there arises a need to create low pump powers and still have less losses. This was made possible by using a resonator cavity and a pin diode. When a reverse bias is applied, the TPA-induced free carrier absorption loss is decreased. The main advantage of using Raman lasers is spectral flexibility, which implies we can get any output wavelength by choosing a pump wavelength appropriately. Epitaxy is a fabrication process where new crystalline layer is deposited on a substrate. It is mainly used to make BJTs and CMOS transistors. Under specific circumstances, we can also induce lasing action. For example, take germanium and silicon lasers. Germanium also has indirect bandgap similar to silicon, but in germanium there is a high chance of radiative recombination as compared to silicon. When germanium is grown on silicon, a thermal stress is developed due to high thermal coefficient of germanium. This is advantageous when surrounded by a N region. Electrons are filled up and this assists in radiative recombination. This has led to continuous wave room temperature germanium on silicon lasers. Due to the strain in germanium, luminescence efficiency is also increased at high temperatures and injection levels. Hybrid lasers are fabricated using silicon and group 3 and 5 semiconductor materials. These lasers were developed to address the lack of a silicon laser to enable fabrication of low-cost, mass-producible silicon optical devices. The photoluminescence can be activated either by using a laser or by passing electricity through it. When silicon waveguide width increases, it allows for the integration of different lasers and amplifiers onto the same chip. In recent years, many types of hybrid lasers were developed. One such laser is the sub-milliampere continuous wave laser. It has achieved threshold currents as low as 350 microamperes. On the same silicon waveguide, we can also create a wavelength division multiplexing source by integrating 4 devices with different cavity lengths. The challenges associated with lasers on silicon is to improve power efficiency, lower optical losses, and operate at high temperatures. It also has many opportunities. Work on silicon LED is near to realization. If a trade-off between efficiency and lifetime is found, then silicon lasers will slowly enter every field of science. Optical sensors are devices that use light and generate electronic signals. Widely used sensor is the fog or fiber optic gyroscope. It uses Sagnac effect and senses changes in angular velocity. However, it uses the principle of interference of light for its operation. As it has no mechanical parts, it is indifferent to changes in gravity or vibrations. It uses interference on two counter-propagating light signals which cause a phase shift and hence leading to sensing of angular velocity. The past few years have given rise to a new type of waveguide known as silicon nitride waveguide, which have very less propagation loss. These waveguides, when used in a sensor, help in increasing the sensitivity. The main problem with fog is polarization rotation. This is because optical fibers allow two polarization modes, but the silicon nitride waveguides propagate only transverse electric mode or TE modes. Whenever there is a waveguide crossing or there is a transition from silicon nitride to silicon waveguide, then there is a chance for reflection which leads to transmission loss. This can be reduced if there is a transition to a second layer of silicon nitride waveguide. Hence a trade-off can be managed between coupling efficiency and waveguide crossing loss which can benefit the sensor. Currently, research is being done to reduce the volume of sensor to less than 1 centimeter cube. Integration of feedback systems is also being done so that we can calibrate the sensor and correct any spurious offset accordingly. Such sensors can be used for navigation and military purposes. Thank you.